So we are going to look at and consider oxygen binding to myoglobin. So what we're going to see with this situation is we have what's called a hyperbolic binding curve, and that has to do with the shape of the curve that we see here, where it's a hyperbola. It's hyperbolic. Well, I'd be doing a disservice if I didn't do what I always tell you to do when you look at a graph, is make sure you look at the axes so we understand what's being plotted versus what. So what we can see here is YO2. Okay, and we're going to define this as fractional saturation. So this represents essentially the fraction of myoglobin that's bound to oxygen as a function of the whole, the concentration of myoglobin plus the concentration of myoglobin that's bound to oxygen. So that's what that fraction is. So it just represents the amount of the population of myoglobin that's bound to oxygen. And on our x-axis here, we essentially have the concentration of oxygen. Remember, we can measure concentration of gases as partial pressures. So this is the concentration of oxygen. So this is the partial pressure of oxygen. It's measured in torr, and we're going to think about this, and this will make sense when we kind of pull this all together. We're going to think about this as being a property of the environment. So this property of the environment changes because our environment changes. So two numbers that I want you to know is, well, what's the concentration of oxygen when we're in the tissues versus what's the concentration of oxygen when we're in the lungs? So the PO2 value for the lungs, where it's considerably higher, is going to be about 100 torr. And then the concentration of oxygen in the tissues, where we're much further away from our active breathing process, is going to be about 30 torr. So those are two numbers that I want you to remember, and we're going to use this as a way to think about binding events. Okay, so let's think about, again, what this curve shows and see if it makes sense here. So what this is saying is if we have a very low concentration of oxygen, we have a low fractional saturation, and that makes sense. If we don't have a lot of oxygen around, we're not going to have a lot of oxygen binding to myoglobin. And as we increase the concentration of oxygen, we're going to increase the fractional saturation, the amount of myoglobin that's bound to oxygen, until we get close to 100%. But again, we're going to see right here, we're not at 100% yet. Again, we have to take that line way out in order to get close to 100%. But one thing to point out is, again, this importance of seeing something at our halfway value. So I'm going to highlight this line right here. This represents a fractional saturation of 50%. Okay, and this is a special value that we call the P50 value. So the P50 value, okay, we can define as the concentration of oxygen you need to be at for half of your myoglobin molecules to bind oxygen. Okay, so this is the PO2. So it's the PO2 to be at for half of your myoglobin molecules, your myoglobin protein molecules, to bind to oxygen. And always remember that this is a population situation. So it's, in this case, myoglobin 1, that's a monomeric protein, binds 1 oxygen. So it is a 1-to-1, but this is going to be an important thing when we move on and see how this translates to what we think about with hemoglobin. Hemoglobin is a tetrameric protein. So what we're going to see here is that fractional saturation represents the fraction of a population of hemoglobin molecules. And here it's only a monomer, so there's not really anything to think about in that case. But one thing to point out, when we see this hyperbolic sort of shape here, this is an important signal that the binding event is what we call non-cooperative. So it's non-cooperative. So non-cooperative binding event. When we have a non-cooperative binding event, we see this shape, this hyperbolic binding curve. Okay? not going to make a lot more sense until we look at hemoglobin and we see a sigmoidal binding curve, and we talk about why that is. But the shape of these curves are going to become important for understanding the cooperativity or lack thereof in our binding events. So hyperbolic binding curve, non-cooperative, that's what we see for myoglobin. Okay, so I want to pull this all together here and highlight what we see in relationship to other things that we've talked about. And this is going to tie into the fact that I sort of talked about this property of the environment piece. Okay, so we're going to have 3 little stories that we'll kind of wrap up here. We're going to talk about a certain condition. We're going to talk about what is the property of the environment that we're talking about, and then what is the property of the molecule. And hopefully that'll still make sense as we sort of tie these pieces together. So the first thing that we talked about where we introduced these terms, property of the environment and property of a molecule, was protonation state. In that case, the property of the environment was pH and the property of the molecule was pKa. And we could compare those two to determine whether or not a molecule was protonated or not. Bigger number wins in that scenario. If pH is greater than pKa, the environment wins, it takes the proton away from that molecule, and that molecule is deprotonated. So we could do a pH versus pKa comparison to kind of see whether or not a molecule was going to be protonated or not. The next time we sort of talked about this, we talked about the protonation state of proteins. So this is still going to be the protonation state, but now we're talking about it with regards to proteins. And we talked about it with creating a situation where a protein would have no net charge. And what we talked about for that is the property of the environment was still the pH, but now the property that we talked about of the molecule of our protein was pI. And in this way, we defined pI as the pH you need to be at for your molecule to have no net charge. Now again, each one of these represents halfway points, because remember, when pH equals pKa, when we are at the pH of the pKa of the molecule, we defined pKa as the pH you needed to be at for half of your population of molecules to be protonated, right? Similarly, pI is the pH that you need to be at in order for half of your molecules, or I should say your population of molecules, to have no net charge, which means we've got half of them pluses and half of them minuses. Okay, so the last piece in tying in what we sort of talked about here is the condition that we're going to be talking about is ligand binding. And that's really what's happening here. Okay, we're going to see ligand binding throughout the course here. But in this case, we're just looking at a very simple situation where it's the reversible binding of oxygen as a ligand to our protein, hemoglobin or myoglobin. And so the property of the environment is really going to be whatever your ligand concentration is. And in our specific case here, we're talking about PO2. So that's going to be sort of that specific application here. But we can really reflect this with lots of different ligand concentrations. We're going to have lots of different things where we'll talk about kind of ligand binding and binding curves here. So the specific property of the molecule that we talk about here is P50, okay? And in this case, we want to think about if our PO2, if our environment has a higher concentration than the requirement for binding, that P50 value, then we're going to have our molecule binding its ligand. So relating this to myoglobin here, if PO2 is greater than P50, then we will have more than 50% of our molecules of hemoglobin bound to oxygen. Okay, so we're doing again a P50 versus PO2 comparison. If we're talking about this very generally, okay, with just a ligand binding to its molecule, we call this a KD value. So we can define KD, that's a dissociation constant. It's an equilibrium constant for a dissociation reaction. But KD values are really important in biological systems because we can look at KD and that tells us the concentration of ligand we need to be at to have half of our populations of molecules bound to that ligand. So the smaller the KD value, the more that likely we are to have our molecule bound to ligand, because our environment is likely to have reached that minimum threshold. Okay, so hyperbolic curves, hyperbolic binding curves, using the example of myoglobin binding to oxygen, but seeing a lot of different scenarios here where we can relate the property of an environment to the property of a molecule to understand a certain biochemical condition.